Hello. For the next bit, I'm going to hand you over to Luis, who's previously a machine learning engineer at Google and currently a Stellar Udacitian.
Thank you, Matt. Hello. Yes, I'll be introducing you to perceptrons, the base unit of neural networks.
And then I'll be back to show you how to implement.
Now, let's say we're the admissions office at a university and we're trying to figure out which students to admit. We're going to admit them or reject them based on two pieces of information: an entrance test we provide them and their grades from school. So for example, here we have student 1 with scores of 9 in the test and 8 in the grades, and that student got accepted. We also have student 2 with scores of 3 in the test and 4 in the grades, and that student did not get accepted. And then a new student comes in, student 3. This person has scores of 7 and 6, and the question is, should we accept them or not? So to decide this, let's first put them in a grid where the x-axis represents the score on the test and the y-axis represents the grades. Here we can see that student 1 would lie over here in the point with coordinates 9, 8, and student 2 would lie over here in the points with coordinates 3 and 4. So in order to see if we should accept or reject student 3, we'll try to find a trend in the data. For this, we look at previous data in the form of all students we've already accepted or rejected. It turns out that the previous data looks like this. The green dots represent students that we've previously accepted, and the red dots represent students that we've previously rejected. Okay, so time for a quiz. To answer this question, let's look closely at the data. It seems that the red and green dots are nicely separated by a line. Here's the line, and we can see that most points over it are green, whereas most points under it are red, with some exceptions. So that line is going to be our model. And from now on, every time we get a new student, we check their scores and plot them in this graph. If they end up over the line, we predict that they'll get accepted. And if they end up below the line, we predict that they'll get rejected. So since student 3 ends up here, at the point with coordinates 7 and 6, which is over the line, we conclude that the student gets accepted. So if you said yes, that's the correct answer. This method is known as logistic regression. And now the question is, how do we find this line that best cuts the data? So let's look at a simple example. How do we draw the line that best separates the green points from the red points? Well, again, a computer can't really eyeball the line, so we can start by drawing a random line like this one. And now given this line, let's randomly say that we label the region over the line as green and the region under the line as red. So just like with linear regression, we'll first try to see how bad this first line is. A simple measure of how bad the line is just the number of errors. That is, the number of misclassified points. This line misclassifies 2 points, one red and one green. So we'll say it has 2 errors. And again, like with linear regression, what we'll do is move the line around, trying to minimize the number of errors using gradient descent. So if we move the line a bit in this direction, we can see that we start correctly classifying one of the points, bringing down the number of errors to 1. And if we move it even more, we correctly classify the other one of the points, bringing down the number of errors to 0. In reality, in order to properly use the gradient descent method, it turns out that the number of errors is not what we need to minimize, but instead something that captures the number of errors, called the log loss function. Let's actually study that in more detail. So here are our 6 points again, with 4 of them correctly classified, 2 red and 2 green, and 2 of them incorrectly classified, 1 red and 1 green. The error function will assign a large penalty to the 2 incorrectly classified points and small penalties to the 4 correctly classified points. We'll actually learn the formula for the error function in the class. Now we obtain the error function by adding all the errors from the corresponding points. Here we obtain a large number since the 2 misclassified points add a lot to the error function. Now the idea is to jiggle the line around to minimize this error. So if we move the line in this direction, we can see that some errors decrease and some slightly increase. But in general, when we consider the sum gets smaller since we've correctly classified the 2 points that were misclassified before. So the point of this process is to find the best line fit by minimizing the error function. And how do we minimize the error function? Again, with gradient descent. So once more, here we are at the summit of Mount Everest. We're quite high up because our error is large. Here you can see how the height is the sum of the green and red areas. So we explore around to see what direction brings us down the most, or equivalently, what direction can we move the line in order to reduce the error the most. And we decide to take a step in that direction. So now we're misclassifying only one of the points. We can see how that decreases our error function, bringing us down the mountain. And we do it again. We take a step in the direction that reduces the error the most. Now we're at the bottom of the mountain since we reduced the error to its minimum possible value. Okay, so let's look more carefully at this model for accepting and rejecting students. Let's say we have a student 4 who got 9 in the test, but 1 on their grades. That student gets accepted according to our model since they are over here on top of the line. But that seems wrong since a student who got very low grades shouldn't get accepted. So maybe it's too simplistic to think that this data can be separated by just a line, right? Maybe the real data should look more like this, where these students who got a low test score or low grades still do not get accepted. So it seems that a line won't cut it anymore. What's the next thing after a line? Maybe a circle? A circle could work. Maybe 2 lines? That could work too. Let's go with that. Let's go with 2 lines. And how do we find these 2 lines? Again, we can do it using gradient descent to minimize a similar log loss function as before. This is called a neural network. Now the question is, why is this called a neural network? Well, let's say we're working in a very slow computer which can only do one thing at a time. So it's not easy to just ask, is this point in the area bounded by these 2 lines? We have to split it into separate questions. The first question is the point over the blue line? Let's answer that question based on the 4 black points in the graph. We can see that for these 4 points, the answers are yes, yes, no, and no. The second question is the point over the orange line? And we can see that for the 4 points, the answers are no, yes, no, and yes. Now the third question will just take the answers from the previous 2 and combine them. So the third question is, are the answers to questions 1 and 2 both yes? And we can see that for these 4 points, the answers are no, yes, no, and no. So they are all no except for the one that is in the green area. Now let's graph each question as a small node. The first question is the point over the blue line? We have a node with the area and 2 input nodes, the test score and the grades. For example, we have a student where the test score is 1 and the grades are 8. The node plots the point and checks if the point is on top of the black line and returns the answer, yes or no. The second question is similar. We input test and grades, and the corresponding node will plot the point and return a yes or a no depending on the point being on top of the orange line or not. Now the third question, are the answers to questions 1 and 2 both yes? We'll just take as inputs the answers to the 2 previous questions and return a yes if the 2 answers are yes and a no otherwise. This is known in logic as the AND operator. Now this is where the magic happens. If we join the nodes for these 3 questions, then we get a neural network. And if we clean it up a bit, we have the following. The first column is where we input test and grades. And the second column is where we check if the point with coordinates corresponding to the test and the grades is on top of each one of the lines. And the third layer, in which we look at the answers from the previous layer and join them with the AND operator. So this is how our neural network will look. Now you may be thinking, something's a little suspicious here. The first 2 nodes look like they take values and check if the corresponding point is on top or below a certain line, whereas the third node just takes yes or no and returns yes or no. Is it possible to see the third node as one of the first 2? And the answer is yes. So let's look at the AND operator in more detail. Let's actually make a little table of what goes in and what goes out. So in the AND operator, if we input a yes and a yes, we get a yes. If we input a yes and a no, we get a no. If we input a no and a yes, we get a no. And finally, if we input a no and a no, we get a no. Now we can think of a yes as a 1 and a no as a 0. In that case, our table turns into this other one. And now, look at this operator in which we enter values 0 and 1 and check if the corresponding point with those coordinates is over or below the line. If we look at the points with coordinates 1, 1, we get that this point is over the line on the green or positive region, so we get a 1. Now if we look at the points with coordinates 1, 0, we see that it's under the line on the red or negative region, so we get a 0. Similarly, for the point with coordinates 0, 1, this point is under the line, so we get a 0. And finally, the point with coordinates 0, 0 is under the line too, so the answer is 0 again. So this is how our final neural network looks. On the left, we have what's called the input layer, where in this case we're inputting the test scores and the grades. Here we have a case where the test score is 1 and the grades are 8. Then this goes through a middle layer called the hidden layer, which will help us with our computations. So in here we can see that the 1 and the 8 become the point with coordinates 1, 8 on the two graphs in the next layer. In the top node, the point 1, 8 is on the green or positive region, so the top node emits a yes. In the bottom node, the point 1, 8 is on the red or negative region, so the bottom node emits a no. Now we remember that a yes is represented by a 1 and a no is represented by a 0. Now the next layer, called the output layer, takes the values coming out of the middle layer, namely the 1 and the 0, and it locates the point with coordinates 1, 0. This point is in the red or negative region of the final node, so the output here is a no. Thus the neural network has received as inputs the values test equals 1 and grades equals 8, and it has outputted a no. This is a simple neural network, but you can see how adding more nodes in the middle or even more layers of nodes can help us map more complex areas in the plane or even in 3 dimensions or higher dimensional spaces. Neural networks are a very powerful machine learning algorithm used in most state-of-the-art projects such as facial recognition, voice recognition, playing chess, and self-driving cars. And we call it a neural network because these nodes resemble neurons in the brain. A neuron will take as input the output of other neurons in the form of nervous impulses and decide to fire a nervous impulse or not. In our case, the neuron takes as input the output of other neurons in the form of numbers and decides to return a 1 or a 0. Okay, so before we continue with other algorithms, let's do a little aside. Let's say we found ourselves on top of a mountain, Mount Everest, and our goal is to get to the bottom of the mountain. So what strategy can we use? Well, we can do it step by step. We look around us in all the possible directions we can go and find out which direction will get us to descend the most. In this case, it's this direction over here. So we take one step in that direction. And then we restart the process. We look around us and see in which directions we descend the most and take a step in that direction. And we continue this process until we descend the mountain. This algorithm is called gradient descent, and we'll be using it extensively in machine learning. You can think of the mountain as the problem you want to solve, and the bottom of the mountain as the solution. And our process to solve the problem is to take tiny steps in the correct direction that will get us to the solution.
Now we know how to get an output from a simple neural network like the one shown here. We'd like to use the output to make predictions, but how do we build this network to make predictions without knowing the correct weights beforehand? What we can do is present it with data that we know to be true, then set the model parameters, the weights, to match that data. First, we need some measure of how bad our predictions are. The obvious choice is to use the difference between the true target value, y, and the network output, y hat. However, if the prediction is too high, this error will be negative, and if the prediction is too low by the same amount, the error will be positive. We'd rather treat these errors the same. To make both cases positive, we'll just square the error. You might be wondering, why not just take the absolute value? One benefit of using the square is that it penalizes outliers more than small errors. Also, squaring the error makes the math nice later. This is the error for just one prediction though. We'd rather like to know the error for the entire data set. So we'll just sum up the errors for each data record, denoted by this sum over mu. It's this U looking guy here. Now we have the total error for the network over the entire data set. And finally, we'll add a 1/2 in front because it cleans up the math later. This formulation is typically called the sum of the squared errors, SSE for short, because, well, it is the sum of the squared errors. Remember that y hat is the linear combination of the weights and inputs passed through the activation function. We can substitute it in here, then we see that the error depends on the weights, wi, and the input values, xi. As I said before, the data records are represented by the Greek letter mu. You can think of the data as two tables or arrays or matrices, whatever works for you. One contains the input data, x, and the other contains the targets, y. Each record is one row here, so mu equals 1 is the first row. Then to calculate the total error, you're just scanning through the rows of these arrays and calculating the SSE, then summing up all those results. The SSE is a measure of our network's performance. If it's high, the network is making bad predictions. If it's low, the network is making good predictions. So we want to make it as small as possible. Going forward, let's consider a simple example with only one data record to make it easier to understand how we'll minimize the error. For the simple network, the SSE is the true target minus the prediction, y minus y hat, and squared and divided by 2. Substituting for the prediction, you see the error is a function of the weights. The weights are the knobs we can use to alter the network's predictions, which in turn affects the overall error. Then our goal is to find weights that minimize the error. Here is a simple depiction of the error with one weight. Our goal is to find the weight at the bottom of this bowl. Starting at some random weight, we want to make a step in the direction towards the minimum. This direction is the opposite to the gradient, the slope. If we take many steps, always descending down the gradient, eventually the weight will find the minimum of the error function. And this is gradient descent. We want to update the weight, so a new weight, wi, is the old weight, wi, plus this weight step, delta wi. This Greek letter delta typically signifies change. The weight step is proportional to the gradient, the partial derivative of the error with respect to each weight, wi. We can add an arbitrary scaling parameter that allows us to set the size of the gradient descent steps. This is called the learning rate, signified by the Greek letter eta. Calculating the gradient here requires multivariable calculus, which you might already know since we're taking partial derivatives. I wouldn't worry too much if you don't understand what I'm doing here. It's more important to understand the concept of gradient descent and the final result. If you need a refresher, I suggest Khan Academy's multivariable calculus lessons, which I'll link to for your convenience. Writing out the gradient, you get the partial derivative with respect to the weights of the squared error. The network output, y hat, is a function of the weights. So what we have here is a function of another function that depends on the weights. This requires using the chain rule to calculate the derivative. Here's a quick refresher on the chain rule. Say you want to take the derivative of a function p with respect to z. If p depends on another function q that depends on z, the chain rule says you first take the derivative of p with respect to q, then multiply it by the derivative of q with respect to z. I like to envision this as normal fractions. The dq's in the denominator and numerator cancel out, and you get back dp dz. This relates to our problem because we can set q to the error, y minus y hat, and set p to the squared error, and then we're taking the derivative with respect to wi. The derivative of p with respect to q returns the error itself. The 2 in the exponent drops down and cancels out the 1/2. Then we're left with the derivative of the error with respect to wi. The target value y doesn't depend on the weights, but y hat does. Using the chain rule again, the minus sign comes out in front, and we're left with the partial derivative of y hat. If you remember, y hat is equal to the activation function at h, where h is the linear combination of the weights and input values. Taking the derivative of y hat, and again using the chain rule, you get the derivative of the activation function at h. times the partial derivative of the linear combination. In the sum, there is only one term that depends on each weight. Writing this out for weight 1, you see that only the first term with x1 depends on weight 1. Then the partial derivative of the sum with respect to weight 1 is just x1. All the other terms are 0. Then the partial derivative of this sum with respect to wi is just xi. Finally, putting all this together, the gradient of the squared error with respect to wi is the negative of the error times the derivative of the activation function at h times the input value xi. Then the weight step is the learning rate, eta, times the error times the activation derivative times the input value. For convenience and to make things easy later, we can define an error term, lowercase delta, as the error times the activation function derivative at h. Then we can write our weight update as wi equals wi plus the learning rate times the error term times xi. It's the value of input I. You might be working with multiple output units. You can think of this as just stacking the architecture from the single output network, but connecting the input units to the new output unit. Now, the total error would include the error of each output summed together. The gradient descent step can be extended to a network with multiple outputs by calculating an error term for each output unit, denoted with the subscript j. Next, I'll show you how to translate this into code so you can implement gradient descent in Python and NumPy. We saw before with the XOR perceptron that adding a second layer of units allows the model to find solutions to linearly inseparable problems. So here is an example of a multi-layer perceptron with 3 input units, 1 output unit, and 2 units in the middle. This middle layer is called the hidden layer. Calculating the output of this network is the same as before, except that now the activations of the hidden layer are used as the input to the output layer. The input to the hidden layer is the same as before. It's these weights times the input values plus some bias term. And as before, again, you use an activation function, such as a sigmoid, to calculate the output of the hidden layer. The hidden layer activations are passed to the output layer through the second set of weights, and again, use an activation function to get the output of the network. Stacking more and more layers like this helps the network learn more complex patterns. This is where deep learning gets its name from, and what makes it so powerful: deep stacks of hidden layers. Now we're dealing with multiple layers, and we'd still like to train the network with gradient descent. From before, we know how to calculate the error in the output node. We can use this error with gradient descent to train the hidden to output weights. But to train the input to hidden weights, we need to know the error caused by the units in the hidden layer. How do we find these errors to use in the gradient descent step? Before, we found the errors by taking the derivative of the squared errors with respect to the weights between the input and output layers. If we do that with the hidden layer using the chain rule, we find the error for units there is proportional to the error in the output layer times the weight between the units. And this makes sense. A unit with a stronger connection to the output node is going to contribute more error to the final output. Here you see the error times the weights. This is the same way you propagate inputs through the network. The inputs times the weights between the layers. Instead of propagating the inputs forward, you're propagating the error backwards through the network. Now you can view this process as flipping the network over and using the error as the input. This method is called backpropagation. And this process works the same when you add more layers. You just keep propagating the errors through the layers. Backpropagation is fundamental to how neural networks learn. So it's really important to understand this if you're going to be building deep learning models.